Hello everyone, and thank you for joining us for today's Surface Measurement Systems online webinar. Today we will be exploring the topic, experimental methods for measuring vapor pressures of chemical substances. We're lucky enough today to have our very own Dr. Vladimir Martis delivering today's presentation. Our resident expert in vapor pressures, Dr. Vladimir Martis is the DVS product manager for porous materials and vacuum product specialist at Surface Measurement Systems. He received his master's degree in materials engineering from Trenčín University of Alexander Dubček in Slovakia in 2004. He received his engineering doctorate degree in molecular modelling and material simulation from the chemistry department at the University College of London in 2012. Since joining SMS, Dr. Martis has continued working on the development of advanced in situ experimental surface science techniques using molecules as probes instead of X-rays for studying catalysts, zeolites, MOFs, polymers, freeze and spray dried materials, composites and glasses under relevant industrial conditions. Dr. Martis has authored several papers in peer-reviewed journals and presented at several international conferences. Now, before we pass over to Dr. Martis to begin his presentation, I just want to remind everyone of a few housekeeping rules before we proceed. If you could all keep your mics muted for the duration of the presentation, please, just to avoid any feedback from anyone else's end. And as you may know, at the end of today's session, we'll have a live Q&A with Dr. Martis, so you can pose any questions you have on this topic and any other questions that arise from the presentation. You can submit these questions in one of two ways. You can submit them in writing at the questions tab, where I will pick them up and ask Dr. Martis in person at the end of the session. Or alternatively, you can raise your hand, and at the end during the live Q&A, I will let you know when you can unmute your microphone and you can ask Dr. Martis your question yourself. So just to reiterate, you can submit your question for us to ask in the questions tab in writing, or you can ask the question yourself over your mic just by raising your hand and waiting for us to call you up. So without further ado, I will hand the control over to Vladimir to begin his presentation. Thank you, everyone.
Well, thank you, John. So good afternoon, everyone, and thank you very much for dialing in this afternoon. Now you should be able to see my screen.
Yes, we can, Vlad.
Thank you, John. Yes. So thank you once again. Thank you very much for dialing in today and join this afternoon webinar about exploring the experimental methods for vapor pressure measurements. So first, I'm going to just give a short introduction to the vapor pressures. It's just one slide is quite busy. So basically, let me define first the vapor pressure. So the vapor pressure is defined as the pressure exerted by vapor in thermodynamic equilibrium with its condensed phase. The given temperature in your closed system. This can be as a sample, as a substance can be either solid or liquid. The value of the vapor pressure are then used to calculate the heat of vaporization or sublimation. Now, the vapor pressure of a substance at a certain experimental temperature is usually characteristic of material, which can be defined by its properties like molecular mass, melting point, and boiling point. The vapor pressure doesn't really depend on the amount of liquid or solid samples, as long as we can use only a small amount of liquid or gas specimen, because that's going to be only the present in equilibrium with this vapor phase. Typical applications for vapor pressures are either the environmental or human health protection, vapor pressure deposition processes, lubricants in semiconductors, vacuum industry, heat transfer fluids, fragrance formulation, photovoltaic production processes, aerospace, and automotive industry. Now, let's move on to my next slide, where I'm going to explain the vapor pressure of liquid, what it is. So let me give you an example in which you have already observed the phenomena of vapor pressure at home. So we all heated up the pan, filled it with the water, and with the closed lid on the top on a gas cooker. And many times you forget about it. So you are in the middle of something, you're doing something else. And what you observe you hear some rattling noise from you hear some rattling lid, and the hot water is spilling out of the cooker. So what we observe here is the form of the thermodynamic point of view is we're observing that the liquid is heated up and its molecule obtain enough kinetic energy to overcome forces holding in the liquid, and they're escaping into the gas phase. So during this process, what's happening as they're escaping, they generate enough pressure to move the lid up, which allows the vapor to escape. So, as the vapor show, so once these gas molecules form, which creates the population of molecules in the gas phase, in the vapor phase above the liquid, this produces pressure, and the pressure is and this is called the vapor pressure of the liquid. Now, the other important parameter is the relationship between volatility and the boiling point. So volatility describing generally how readily a substance vaporizes. So we have the table here which shows different compounds varying from boron to hydrogen. But what we can see from these tables is as the boiling point is going down, the volatility goes up. So hydrogen is very highly volatile compared to, let's say, mercury, and which is the least volatile. And one of the use of the mercury was in the manometers, in the YouTube shape manometers, because the vapor pressure of the mercury is about like 0.0017 torr at 25 degrees Celsius. As you know, the vapor pressure is also strongly correlated with the temperature. So the vapor pressure exponentially rises with increasing the temperature. And if you use natural logarithms to express this nonlinear relationship as a linear, we can use this Clausius-Clapeyron equation where LNP is equal to heat of vaporization, or the universal gas constant R, and temperature T, and the C is the slope, intercept is the constant for the equation. Now, there are several methods to measure the vapor pressure. So here we're looking at the table which was produced by OECD guideline, showing different methods for the vapor pressure. So you have the dynamic method, static method, the effusion method, or gravimetric method. In these talks, and each of these methods got its own certain recommended range, and also the reproducibility range, whether they're suitable for liquids and solid. Now, in these talks, I'm going to focus mainly on that's an effusion method, which is applicable in the range 10⁻⁻15 Pascal up to 100 Pascal, and the static method, which is direct measurements of the vapor pressure, which can be applied in the vapor pressure range from 100 to 100,000 Pascal. The reason we have to use these two methods in order to cover whole vapor pressure range, because shortly you won't be able to, if the effusion rates or the evaporation rates is very high, then you won't be able to use the Knudsen effusion method because your sample is going to evaporate fast, completely, before you'll be actually able to measure. So let's start with Knudsen effusion method. So the Knudsen effusion method is a gravimetric method. So what it means, so we're using the thermal balance to measure the effusion rate of molecule into the vacuum. In this measurement, sample is held in a small Knudsen cell, which is called Knudsen, which is a small orifice, and the molecule escaping through that orifice into the vacuum. Now, this tells is a place inside to the metal pan, and then that metal pan is hanged from the ultrabalance onto the hang down wire. So what we measure during these measurements is the constant mass loss. And as you know, the effusion rate or evaporation rate is proportional to the actual vapor pressure of material. So we continuously measure the mass loss of the sample during this process. So as you can see, as a function of the time, the constant temperature, what you see, we observe in the muscle, which is usually the linear. So what these nut cell look like? So on the picture here on the top, we have the lid, and with a small orifice size, and at the bottom is the cups where it's going to be placed your powder, solid, or a liquid. On the right side, you have the insert of the view. So once you load the sample, we screw the lid on top of the cup, and we place the Knudsen cell into the metal pan, and then we hang it directly from the hang-down wire, which is suspended from the ultra balance. And this is also all placed inside the vacuum chamber, and then we just pull the vacuum. So during the measurements, we continuously weigh the sample, and we measure the mass loss rate under the high vacuum at the different temperatures. So how we can calculate the vapor pressure of material from the Knudsen effusion method? So you expose the sample to a certain temperature. Basically, temperature, in a closed environment, temperature defines your evaporation rate. And from this evaporation rate, which is expressed as dmdt value, we can calculate the vapor pressure using classical Clapeyron equation. So for calculation of vapor pressure, we're going to use this equation on the right. And for this, we need to have knowledge of the molecular weight of the sample. So this is very important. The surface area of the orifice, and the dmdt value or the evaporation rate, which is obtained from these thermogravimetric measurements at different temperatures. So the dmdt value is obtained at least for 5 different temperatures, and during these measurements we obtain linear mass loss, and then we feed that value here, and we automatically calculate the vapor pressure of the solid at a experimental temperature. Now, for this method, we're using the apparatus, which is called vapor pressure analyzer. So what we have here, so we have the temperature enclosure, which allows us to control the temperature in the temperature range between 10 to 80 degrees. Inside, we have the vacuum stand, and under the dome here, we have ultra balance. From the balance beam, we are suspending hang down wire, and on the left-hand side, we have the sample. So in this case, the sample is placed inside the Knudsen fusion cell. On the right side is reference to counterbalance the sample side. And this is connected to the vacuum line. And at the end of the vacuum line, we have the set of the turbomolecular pump and the rotary pump to maintain a very high vacuum. And the pressure is measured using the vacuum pressure gauge. So this is the typical setup for this measurement. Now, some of the samples, especially the oils, they're not going to evaporate at low temperatures, below 80. So if we have this kind of samples, what we do, we increase the temperature of the sample locally to, let's say, 400 degrees, and we measure the evaporation rates at different temperatures, let's say from 80 up to 300 degrees Celsius. With that valid temperature at each temperature at least for 2 or 3 hours. So this is the typical setup for the measurements of Knudsen effusion method. So here's just a brief picture of the system. What we have here is the set of the pumps. Here's the temperature enclosure, and inside is the vacuum system. It's a fully automated system controlled by PC, where we run just automated method to run the different measurements. So let's move to the example of the Knudsen data. So system is usually calibrated using a reference material like benzoic acid because its vapor pressure is well known. So in typical experiments, so once you load the sample into the Knudsen cell, we pull high vacuum, and then we expose the sample to different temperatures, and we wait at each temperature for several hours. So in this case, we waited about 3 hours at each stage. So I call each these temperature steps a stage. So solid line is from the incubator, solid yellow is from the preheater. So in this case, the preheater is just measuring the temperature of the sample under the Knudsen cell. And what you observe, as you expect, as we increasing the temperature, the effusion rate or the evaporation of rates of the molecule is faster. Now, and from this data now, so then you have the evaporation rates at different temperatures. From this data now, we can calculate using the equation which I showed earlier, vapor pressure of the benzoic acid at different temperatures. Now, as we do this, we automatically calculate the heat or vaporization using classical Clapeyron equation, and then here we get logarithms of vapor pressure versus inverse temperature. So you expect the heat of vaporization for basic gas is about 88 kilo, about between 88 and 87 kilopascal. Kilojoule. Now, so what's the absolute value of the vapor pressure for this material? So the experimental range was between 30 to 60 degrees. We have the evaporation rates in the column, marked as the MDT. We have the vapor pressure obtained by using our, let's say, diffusion method in this column here, and then vapor pressure with the stars from the literature. As you can see, there is a really good agreement between measured vapor pressures and vapor pressures obtained from the literature of the publications. And also noted the vapor pressure size of the orifice, which was in this case was 167 micron. So we have the cells with different sizes of the orifice, and this is important depending on type of material you use or evaporation rates we expect. So if you have highly volatile materials, you want to use a smaller orifice size. When you have a, let's say, material which is less volatile, like the oils, you want to use a higher orifice size to get a good data. Now, next example is, so basically the data are automatically calculated using our analysis software. So in this case, we generate the report and absolute value, which provides you all the vapor pressure value in the Pascal, as well heat of vaporization in the Joule. So this all automatically. Now I move to do some examples. Let's say vapor pressure of naphthalene. So you might be familiar with naphthalene. You always used to have it to keep the clothes fresh. So basically, the vapor pressure is at 25 degrees. Is a nice linear evaporation rate is about 11.8 Pascal, and the production agency reports 11.6 Pascal. So it's very good agreement. Now, another example of this method is for vapor pressure of the soils like pesticides and fungicide. So these are environmental to tackle the environmental issues. So we look at the 4 different pesticides: ametrine, bifenthrin, chlorac, and azoxystrobin. And again, Knudsen method and the literature values are in very good agreement, and you can go down to 8.7, about 110 minus 10 Pascal. So again, so it's just example of one of these mass data here. So it's very useful method. Again, another interesting application is the vapor pressure of the greases or lubricating oils. And this is mainly for the vacuum palm oil. So, and it may, because the function is for lubrication, cooling, corrosion protection, noise reduction. And one of the requirements is the low vapor pressures. Because if you have high vapor pressure, it's going to, especially the training, it's going to cause the issue with the process. So here, look at the vapor pressure of the oil A. So what we see here, we have the effusion rate on the top graph. When we increase in the temperature, we go from 80 all the way up to 230 degrees, showing the solid yellow line, and the maximum rate of evaporation rate are shown in solid red line. What you observe at low temperatures, we can't measure this vapor pressure because it's so low. So the system, the microbalance is not able to detect it. And then once the temperature is increased above 100 degrees, so we are able to calculate the vapor pressure of this material. That is the total vapor pressure of this oil. Same story applies to the same oil, but is the vapor pressure of oil C. Again, in this case, the vapor pressure measuring range for this oil had to be increased up to 200 degrees, and the measurements were done from 200 degrees to 260 degrees. So in order to get a good evaporation rate. So as you can see, it's very important to find the right temperature. So the vapor pressure, when you extrapolate the vapor pressure to 20 degrees, the value go down to 10 minus 15 Pascal. Now the other implication is vapor pressure of sealants. So here look at the silicone vapor pressure, and what you observe here, it is the other opposite. So in this case, you want to go to lower temperatures because the evaporation rates are quite high at 25 degrees, as you can see here from the evaporation rates on the left-hand graph. So at 25 degrees, you have very high evaporation rate. Then you get to 30 degrees. The change in evaporation is only small, and at 35, also there's no significant change in evaporation rate. But when you increase the temperature all the way to 40 degrees, the sample completely evaporated. So there's nothing left in the pan. So, but we were still, so in the small narrow temperature range between 25 and 35 degrees, we were able to calculate the vapor pressure of this silicone. which was about 3.3 Pascal at 25 degrees. The other application is vapor pressure like basic chemicals, like stabilizers, neutralizers. So here we look at the vapor pressure curve of 3-isopropanolamine, and again, it was measured for narrow temperature range from 40 to 90 degrees. Those ones go higher to temperature evaporate. And then we were able to evaporate extrapolate value for 20 degrees, which was about 0.006 Pascal. Now, so that was all done for the Knudsen effusion method, the gravimetric method. Now I'm going to move to the static method. So static method is a little bit different. So static method, we're going to look at the evaporation and condensation in a closed system. So what we're going to do here, so on the left-hand side, we have the system, we have the flask filled in with the water, connected with the pressure gauge, and on the top we have a thermometer. Okay, so what we measure here, so this is the static method, so there is no moving part. So static, or so in a closed system means that air cannot coming in and water cannot go out at the same. So inside the flask, the water cannot come out and air cannot coming in. So this means closed system is completely isolated. That's why we have this stop plug on the top is thermometer, and it's connected to closed cage. So initially, so when you pour the water, close the valve, we measure the pressure of the dry air in the flask. So the pressure is almost zero. So the rate of evaporation is almost non-existent. Now, if we set the temperature to 20 degrees, the rates of evaporation will increase. So we have the water molecules escaping from the liquid, and when there is enough evaporation, then some of the molecules, then they will start condensation. So the evaporation, so the rates of condensation in this case will be defined by the rates of evaporation. And in general, what we have here, the evaporation will be greater than the rate of condensation for the liquid water. So once what we see here, afterwards, so we will be observed to measure the vapor pressure of the liquid. So as you can see, now the gauge moved. And as a result, the rate of the condensation is increasing. Now, what we're observing, once we reach the rate of evaporation and condensation, we reach the dynamic equilibrium. And that dynamic equilibrium, the both rates will be equal. Okay, so this is how we're going to measure it. And at some point, we will saturate, because it's a closed system, so we're going to measure the saturation pressure of water inside this system. So now, how are we going to do this experimentally? So for this, we have I show the schematic of the static vapor pressure apparatus, which is very similar to what you saw in the previous picture. So basically what you have the liquids filled in the flask. So the vapor pressure is 0. So the vapor pressure, so the liquid might start evaporate at some point after a few minutes. And all this is inside the temperature control enclosure. This is very, very important because the temperature enclosure will define your evaporation rate at a certain temperature, let's say 25 degrees. Then we have the chamber, small chamber, when you have isolated by such of the valves. And then we measure the increase in the pressure. So when we open the valve, we measure the increase in the pressure inside this vacuum chamber using 2 pressure sensors, 10 to 100 and 1000 torr. And all this is set to turbomolecular valve. So what's happening here, prior to the experiments, we remove the air. So this, you cannot measure 3, just to make it clear, you cannot measure 3 samples at the same time. So what we're measuring here, first, we basically outgas solvent number 1. So we open the valve, we pull the vacuum, the pressure will decrease. During the outgassing process, we remove all the air about the molecule till we reach the the rates of the evaporation and condensation are equal. So once we reach that state, we close the valve. We close the valve here, which will isolate the pump, and the pressure inside the vacuum chamber will reach to saturation pressure. Once the experiment is completed, we can repeat the same experiment on the using the solvent number 2. So again, we first do the outgassing of the solvent, and then we close the valve and we measure the vapor pressure. And then we can do the same experiments for the solvent number 3. And this can be done at 3 or 4 different temperatures because the evaporation rates and the vapor pressure will change because of the temperature. So what it looks like, so the solvents looks like this. They are connected directly through the stainless steel flask to the vacuum valve, and then we just evaporating the liquid. So at the bottom, what you see here is the sample 1. So you have the liquid sitting at the bottom. So large surface area gives larger evaporation rate, but the number, the vapor pressure and the liquid in a closed system won't change. So you're not going to get any losses. And then you have the second liquid sitting at the back. Now, first let me show you now an example of the measure. Now, the static vapor pressure method is direct measurement of the pressure. So that's an effusion method, which is gravity method, is indirect measurement. So in this case, once we have done the molecular outgassing, so we close the valve and we observe the vapor pressure. So here's the vapor pressure of cyclohexane at 25 degrees, which was 98.34 Celsius. Another example is vapor pressure of an octane at 40 degrees, and the vapor pressure is about 31.9 torr. Now we can measure also vapor pressure of, let's say, quite highly volatile compound like vapor pressure of cyclopentane at 37.9 degrees, and this vapor pressure is about 511 torr, which is about 68.2 kilopascal. Another example is vapor pressure of the perfluorodecalene at 25 degrees, and its vapor pressure is about 27. As you can see, it's very straightforward the method for the vapor pressure measurement. Also, the main benefit of this method is that it can be applied to the mixtures with the different molecular weights distributions. So in this case, we look at the oligomers. So the system allows you to measure the multiple samples. So in this case, sample 1, we have a vapor pressure of 4.9 torr, and you outgas the vapor pressure sample as well. Now, so this comes to my slides. So I just, in conclusion, I hope I show you enough data to convince you that the both static and Knudsen effusion methods are powerful methods to measure the vapor pressure of various substances, varying from the liquids to solids. And lastly, I would like to thank you for your attention. And if you have any question, please don't hesitate to ask.
Thank you, Vlad. That was very enlightening. We have our first question here, but before we get into that, I would just like to remind our audience that there are 2 ways to submit your questions. Please do so in writing through the questions tab, or you can raise your hand and ask the question over the microphone directly to Dr. Martis himself. So please do so now while we're addressing this other question. Just for now, Vlad, we have the question, what is the best method to measure vapor pressure of volatile materials?
So that's a really good question. So the best method to measure the vapor pressure of volatile material is the static method, because the evaporation rates at ambient temperatures are very high, and it is the easiest way to do the measurement. Because for the static method, we will for Knudsen effusion method, the sample will be evaporating fast before we will be able to obtain any measurable data before obtaining any good vapor pressure data. So static method is the method with the choice.
Great, thank you. We have a hand raised by Takayuki Toyomasu. So Takayuki, I will unmute your microphone now if you would like to unmute yourself and ask your question. We can see you're unmuted, Takayuki, but we can't hear you. Okay, we'll just give him a moment to arrange his microphone. In the meantime, we have another question submitted. Oh no, that's just a thank you from the audience, Vlad, rather than a question. So we'll go back to Takayuki. Takayuki, are you able to ask your question? It looks like he might be having trouble with his microphone. If he is able to, if you're able to hear us, Takayuki, please do submit your question in the questions panel, and we will address it there if you are able to submit there. A question has just come in, Vlad, from a Jason Perman, who also says thank you for a wonderful presentation. And Jason asks, are there any solvents to where you can't measure the vapor pressure?
This is the good question. So we can measure only vapor pressure of solvents which have the vapor pressure within the range given by the measuring method. So if the vapor pressure of the solvents is highly volatile, and it is outside of our measuring range, so let's say it's above 1 bar or 100,000 Pascal, we won't be able to measure it because it's going to be too high for our apparatus. So in general, we can measure the vapor pressure of the solvents using either static or Knudsen method, depending on the solvent's characteristic, which will be defined by the boiling point and also by the molecular weight. So in generally, we can measure most of the solvents, but as I said, it all depends whether it's going to be fit within the vapor pressure range is interested in.
Okay, and would that be the same for an ionic solution? Jason's asked.
The ionic solution, we can measure the vapor pressure of the. We should be able to measure the vapor pressure of the. I'm not sure what's the vapor pressure of the ionic solution. So I mean, in theory, the best way to just to try. If it's, let's say, if the vapor pressure is going to be up to 1 bar, so we should be able to measure it. Or if the vapor pressure, I measured the ionic liquids in the past, and ionic liquids got extremely low vapor pressure. So if you talk about ionic liquids, so the vapor pressure needs to be measured using Knudsen effusion method because it's extremely low, so we can easily measure it. If you're measuring the ionic solution, so this must be probably done using the static method because vapor pressure might be probably higher than 100 pascals. So I'm not sure what. So what vapor pressure do you expect? Let's say 25 degrees for this solution.
Brilliant, thank you. We'll just wait a few more minutes for any more questions to be submitted. Okay, it doesn't look like we have any more questions coming in, Vlad. So I think we can finish up there. Thank you again to our audience for being with us today, engaging Vlad on this webinar. Is there anything you'd like to add before we finish, Vlad?
No, I just would like to thank you to all our attendees that have found the time to join this webinar. And if they have any questions regarding the measurements, or they would like to try to measure vapor pressure of the samples, either solids or liquids, they should get in touch and we can have a discussion. And if possible, I'm happy to do some preliminary work for proof of concept. And once again, thank you very much for your attention.
And thank you, Vlad, for a great presentation. Yes, just further to what Vlad said, if anyone has any requests for any more information about what's been discussed today or wants to engage in taking some vapor pressure measurements, please do contact us at science@surfacemeasurementsystems.com. And we also invite you to attend all our upcoming educational events. We have 2 more webinars coming up this month, one focused on BET surface area measurements by absorption methods at ambient conditions, and this will be taking place in 1 week from today. And we will also be having a webinar on the moisture absorption and drying kinetics by DBS analysis, which will be taking place in 2 weeks' time, 2 to 3 weeks' time. You can find out more about these on our website at www.surfacemeasurementsystems.com, and you can find more info on those in the webinars page. Thank you again to all of our attendees for joining us today, and we hope wherever you are, you have a wonderful afternoon, evening, or possibly even morning. Thank you all and take care.
Thank you, John.